All right. Good morning, everybody. So today we're going to start our final material, talking about amino acids. This is a subject that is kind of near and dear to my heart for the last several years. It's been my research areas on the synthesis of and utilization of unnatural amino acids, but we're going to pretty much stick to the natural amino acids. And I put that in air quotes because it's, you know, you've probably learned there's 20 natural amino acids. There's actually more than that. Technically, it's natural if it appears in nature, right? But we're going to talk about what I call the 20 proteinogenic amino acids, the ones that we quite commonly find in proteins. Now, you'll notice we skipped, in this class, we skipped lipids and we skipped carbohydrates. But I incorporated those biomolecules in various lectures. So we talked about fatty acids at various points, and we talked about sugars at various points. The reason that we, and at least in this class, why we skip those is because you're going to get that when you get to biochem, and we had to make a decision. So I could have either crammed all of those biomolecules into 2 lectures and not given you much of anything, or we could have focused on one of those classes of biomolecules and prepared you better for the beginning of biochem, which is the way that we chose to go. And if and when you take biochem, they're going to expect that you know the 20 proteinogenic amino acids. So that's why we're starting with that information. So today and tomorrow we'll talk about amino acids. Friday we'll have a review, and Monday we have an exam. And so we have exam 3 on Monday. So there is a table in your book. These amino acids are the ones found in proteins. You need to have these more or less committed to memory by the time you get to biochem. Okay? Are you going to have these committed to memory for my exam? Probably not. Okay? But there are some that you need to know. Okay? There are just some that you're going to have to know the structure of. And the first one is glycine. And glycine is the simplest of the alpha amino acids. First, why do we call these an alpha amino acid? That's right. So the amino functional group is alpha to the carbonyl of the, it's on the alpha carbon. So that's exactly right. Now you can have other types of amino acids. You can have beta amino acids. You can have gamma amino acids, delta amino acids. It's a lot of the work that my research group works on how do we synthesize those types of things. We'll talk a little bit more about that later. Now, when you get into biochemistry, you're never going to write out glycine. You're either going to use the 1-letter abbreviation or the 3-letter abbreviation. G for glycine, gly for glycine. Now, I have to admit, I go with the 3-letter code. So that's what you need to know for my exam, the 3-letter code for the amino acids. It's easier for me to remember. I have trouble with the 1-letter code, in part because when we get down to lysine, you'll see that the 1-letter code for that is K. And every time I see it, I think potassium. So it's kind of, I've just never really been able to keep in my memory anyway the 1-letter code. But for some people, it works pretty well. In these types of tables, you'll see the structure. And you'll also see the abbreviations. You'll see the pKa values. And you'll see this thing called PI, which we'll talk about in just a moment when we talk about titrations. So the pK of the alpha carboxylic acid, the pKa of the alpha amino as the ammonium salt. So you'll see those values. If you look at the carboxylic acid values, what can you tell me? What's kind of strange about those carboxylic acid pKa values? They're lower than you would expect, right? You would expect that the pK of a typical carboxylic acid would be somewhere around 3.5 to 4.5, 5, right? Kind of what we talked about for acetic acid. But these are a bit lower. Can anybody tell me why? Why would an amino acid have a lower pKa value for the carboxylic acid function than, say, acetic acid? That's exactly right. You've got that nitrogen on the alpha carbon, and nitrogen is somewhat electron withdrawing, right? And that's exactly right. So you can see the fact that that actually has a substantial effect on the pK values for these carboxylic acids. Now they're all more or less in the same range, depending on, so here we got glycine. There's no substituents on the alpha carbon. It has a pK of 2.3. The amino group has a pK of 9.6. Alanine, now we're getting into chiral amino acids, right? So glycine is achiral. There's no chirality. Here we have a chiral carbon right here, and we say that this is the L amino acid, okay? So all L amino acids have the S absolute stereochemistry with the exception of one of them. They're all L, okay? But the absolute stereochemistry for these amino acids is S except for cysteine, which has a sulfur, and it changes the priority order, okay? So all of these amino acids that we're talking about, the L amino acids, which are considered the natural amino acids, have the S stereochemistry except for cysteine. So here we have alanine. Alanine, one of the hydrogens of glycine is removed and replaced with a methyl group. Valine has an isopropyl group attached to the alpha carbon. Valine's really easy to remember because the side chain looks like a V, right? So that's pretty easy to remember. So valine, then you have leucine, which has a butyl group attached to the alpha carbon, okay? Then you have isoleucine. What does iso mean? Different? Yeah, it's just an isomer, right? So if you look at this, leucine and isoleucine have the same molecular formula. It's just that this methyl group has been moved over here, and now you have two chiral centers in the molecule. So how many possible stereoisomers are there for isoleucine? There are 4 possible stereoisomers, right? 2 chiral centers, 2 squared, right? Phenylalanine has an aromatic ring for its side chain. Tyrosine looks very similar to phenylalanine except it's got a phenol, okay? And then you have tryptophan and you have serine, okay? And again, the pKa's for the carboxylic acids more or less are in line with one another. It looks like phenylalanine's a bit lower, a little out of line with all of these other ones, okay? And so these don't change too much. What's this third value out here for? That's this R group in the side chain. Notice it's not there for these because these have no ionizable groups. But this OH can be ionized, right? I mean, it's an acidic hydrogen, so you can remove that group and do a variety of different things with it. We have threonine. This has how many chiral centers? 2, right? We've got one here. So again, there are 4 isomers for it. We have proline. How does proline differ from the other amino acids? It's cyclic, that's right. And so what type of amine did we have for all of the other previous ones? Yeah, it was a primary amine. Proline, however, is a secondary amine, and it turns out that that's kind of important. So you will find when you start studying biochemistry, when you have a lot of prolines that are close to one another, that usually involves some type of disruption in structure. And so you'll learn about structure function and proline and how that comes into play. You'll see that the pKa of the amino group is a little higher, as you might expect, because it's a secondary amine as opposed to a primary amine. Don't worry about 4-hydroxyproline. We're going to ignore that one. This is cysteine. And so cysteine is a very useful amino acid for a variety of reasons. On Wednesday, we'll talk about how your hair shape, whether or not you have curly hair or straight hair, depends on how your cysteines are actually connected to one another. So we'll talk a little bit about that. But because sulfur has such a high priority, even though this is the L amino acid, it actually has the R absolute stereochemistry, okay? Cysteine is just 2 cysteines that happen to be oxidized together. So we're not going to worry too much about that one today. We'll talk more about that on Wednesday. Methionine. Methionine is somewhat related to cysteine. It's got an extra carbon in it, but it also is what do we call this functional group? This is a thiol. This is a what? That's a sulfide. That's right. So you go from a thiol to a sulfide is methionine. And then asparagine and glutamine. These are amino acids that are useful in a variety of other things as well. So asparagine sounds like what? Asparagus, and that's actually where it was discovered. So asparagus is actually quite high in asparagine, and if you've ever smelled asparagus, it kind of has an amine kind of smell to it, and it's because asparagine will actually decompose slightly into ammonia, and so that's where that comes with. So we also have amino acids that contain acidic side chains, and so you have another pKa that you have to keep in mind. So here's aspartic acid, and again you can see that you have the pKa of the other carboxylic acid group, which is out here. So is that more or less in line with what you'd expect for a carboxylic acid? That's more in line with what you would expect with a carboxylic acid, and that's because it doesn't have an amine on its alpha carbon, right? The amine is here, so this carboxylic acid is a little lower than you might predict for typical carboxylic acid. Okay? Glutamic acid is another acidic one. And then there are also some amino acids that have basic side chains like lysine. So lysine, again, K. I always got that one kind of confused. I always saw that and I think, why is there potassium in the sequence? But it's not. It's just a one-letter code for lysine. So I prefer LYS. And you'll see it has a primary amine out here on the end in addition to the primary amine on the alpha carbon. And so you can see that there is quite a little bit of a difference in the pKa values of these two primary amines. Arginine and then histidine, of course, very, very important types of amino acids that you will find in a variety of different proteins. So these types of basic side groups typically form salts in aqueous solution, and that's useful for controlling the structure of these proteins that they are incorporated into, which we'll talk a little bit more about on Wednesday. So what's this PI value? So I think we all understand the pKa's. We know what a pK of a carboxylic acid is, and amine, whatever the side group is, right? Well, what's PI? What? You can guess. Nope, not solubility. Good guess, though. It's the isoelectric point. Anybody know what that means?
Like where on the molecule the charges, like they cancel out, it's basically no charge.
All right, so that's the point at which you have a zwitterion, right? And so if you think about it, if I take an amino acid and let me blank this out for a second. Let's look up here. So let's look at an amino acid. Well, let's just look at alanine. So NH3 and a methyl group. What pH would that amino acid have to be at to have that charge? I don't need the exact pH, but would it be acidic or basic? Under basic conditions, it would have that charge? Very acidic. So this is low pH. Okay, so at low pH, we would have the amino acid in that charged state. Now, Anna comes along and she starts titrating this amino acid with sodium hydroxide. What's going to happen? What functional group is she going to react with first? The amine? What's the pK of the amine? Oop. The carboxylic acid, it has the lower pKa. The pK of these carboxylic acids is around 2.5, right? What's the pK of the amine? Somewhere around 9.5. So the first thing that's going to get titrated is the most acidic component, right? So that's going to be the carboxylic acid. And if she adds a full equivalent, so if she had a mole of this and she added a mole of sodium hydroxide, what would the resulting structure look like? Oops. Actually, that's not there. What's the overall charge on that molecule? It's 0. So we have plus charge, we have a 0 charge, and now Anna adds one more equivalent of base to this molecule. What's the structure now? Yep, we're just going to deprotonate the amine. The next most acidic component is this, right? And we're going to get the amine as the free base. And what's the overall charge? Negative, right? All right. So now imagine that we take a paper strip and we place it in some type of medium that will conduct electricity. And over here we attach it to the plus side of a 12-volt battery. I don't know, 12 volts sounds good. Over here we place it, we attach it to the negative terminal of the 12-volt battery. So we have a battery. Okay? And we're running an electrical current through it. If I have the pH of the medium that this paper strip is in and I place the amino acid here, and let's say the pH is really low, so the amino acid is positively charged, which way will that migrate on the paper strip? It would move towards the negative electrode, right? It would move just like a TLC moves, and it would find its way over towards the negative terminal. What would happen if we change the pH of the medium that this paper strip is sitting in to, let's say, somewhere around 11 or 12? And so now we have the negatively charged amino acid, right? Which way would that amino acid move? It would move towards the positive. This is called what? This technique is called electrophoresis, and you will do this when you get into biochem lab. This is how you can separate charged species, especially biomolecules, okay? Now, what if we're at a pH such that we have this species? What will happen? It won't move. It's isoelectric. It will not move in an electric field. So where the pH equals the pi value, you will not have mobility of that amino acid. This is how you, in biochemistry or in molecular biology, will separate proteins. By electrophoresis, this is how you separate amino acids, because these species are charged. Okay, and so you can actually separate them based on their charge quite easily. And there's all different kinds of techniques that are actually more interesting than what I've just given you there, but nonetheless, that's it. So let's see what the so for alanine, if we go back to our list, so there's alanine. What value does it have for the pi? 6. How did we come up with that value? Okay, so that's the experimental way. But from this list of data, how would you come up with that PA? Let's suppose I did not have the PI listed up there. What's 9.7 plus 2.3? Divided by 2 is? It's the average of the two pKa values. Okay? So alanine only has 2 ionizable groups. So you just average those 2. But now wait a second. Not all of them are that simple. So let's look at aspartic acid. What's its PI value? What's its PI value? It's 3. So what 2 groups did we average to get 3? Yep. You always average the two most similar pKa values when you have more than one. Okay? So you looked at the two acidic groups, you took the average of those, and you come up with 3. So if the pH is equal to 3 of that medium on that isoelectric strip, it won't move. But if I change the pH one way or the other, then it will start to move in that electric field. Okay? All right. So this is what happens if we have one equivalent. And this is what happens if we add the second equivalent. Okay, these are the extremes. But is that how we do a titration? How do we do a titration? You add little bits, right? And you measure something with the respect to how much of something you add, right? So what we're going to do is we're going to start off with this amino acid at low pH. We're going to look at the hydroxide equivalents on the x-axis. What value are we going to look for on the y-axis? pH. That's right. So we've got some sort of pH electrode. So this is a really simple experiment. So Anna would take an Erlenmeyer flask or beaker. She would put the amino acid in there, add some water, lower the pH pretty low, below 1. And she would put a pH electrode in there. And she hasn't added any base yet, right? So what's the pH going to be? It's going to be really low, right? So when she hasn't added any base yet, the pH is going to be quite low. Now what's going to happen as she starts to add sodium hydroxide? It's going to rise. Is it going to be linear? Or is it going to be kind of curvy looking? What do you remember when you made your titration curves in general chemistry? Kind of curvy, right? It doesn't just go up as a straight line. And so as she starts to add sodium hydroxide, the pH will increase but kind of curvy, and then it will go up to this point right here. What point is that? How many equivalents of sodium hydroxide did she add at that point? She added 1. That's the equivalence point. So 1 equivalent of sodium hydroxide. There's the pH, whatever that happens to be. For alanine, that would be a pH of what? 6? Yep. That would be a pH of 6. We got that from the table, right? And all of her amino acid is now in Zwitter ionic form at the equivalence point. Okay? What is the point right here? That's half the equivalence point, which is also called what? So 1/2 equivalent. You all did this experiment in Gen Chem. I know you did. Not with the amino acid. You did it with something else. Doesn't matter. What's the half equivalence point equal to? No. The pH might be around 3. I'm not going to dispute that. Yeah. But what do we call that value, the half equivalence point? A P? And then a K? And then an A? This is the pKa value, called pKa1. It's the pKa of what functional group? The alpha carboxylic acid group, right. So this carboxylic acid group, pKa, is that value right there. How do I know that? That's true, yep. But how do I know that that point is equal to the pKa? Whose equation do I need to use? Need to use the Henderson-Hasselbalch equation, and I always just call it the HH equation. Henderson I can spell, Hasselbalch I always mess up. This is where the pH is equal to pKa plus the log of A minus over HA for a weak acid. At half equivalence point, what are my values for A minus and HA? So there's A minus and there's HA. At half the equivalence point, what are those values equal to? They're equal to each other, right? So A minus is equal to HA, so this becomes what? 1. And the log of 1 is what? 0. And so at that point, the pH must be equal to the pKa value. That's how all the pKa values that we've talked about have been made, determined, using the Henderson-Hasselbalch equation and some type of titration. Now, for organic molecules, you have to use kind of some special titrations because you can't do some things in water. But this is how we determine pKa values experimentally, by some type of titration. Okay? It just turns out that a lot of the titrations we do today aren't with a burette and sodium hydroxide and a beaker. Okay? But nonetheless, they are some type of titration. You all remember this equation from Gen Chem?
Yeah.
Vaguely? You should remember it quite easily because all it is a rearrangement of Ka. Ka is equal to what? Right? So if we have HA dissociating to give H plus and A minus, Ka is equal to? Yep. This is nothing more than a rearrangement of this. Okay? Somebody just did a little bit of algebra and got their name associated with doing some algebra. Pretty cool, huh? So you just took the acid constant equation, did a little math, lo and behold, everything's fine. Okay? And so the way that you might be able to see this a little better is Ka is equal to H plus over 1 times A minus over HA. So this kind of starts to look like this piece. This starts to look like the pH part, and this would be the pK part. So you take the negative log of both sides, and you can actually derive the Henderson-Hasselbalch equation pretty straightforward from just that simple manipulation. Okay? So that's how we determine that. So now we're at the isoelectric point, or the first equivalence point. Everything is now electrically neutral. And now Anna starts to continue adding sodium hydroxide. So what's going to happen now to the pH? It's going to continue to go up until she reaches that equivalence point. What's going to happen there? It's going to spike up, right? And so here is the second equivalence, right? And you'll be able to figure out what the pH, it's actually going to be quite high there. And then halfway between these 2 points is what? pKa2, which in this case would be the pKa of the amino group, right? And so we would expect that to be somewhere around 9.6, if I remember from the previous slide, okay? They're going to expect you, when you come into biochemistry, to know this stuff very, very well. They're going to start off in biochem by talking to you again about the chemistry of water. And that's really what we're talking about here. This is all in water. You've got to be able to walk into biochem day one understanding this. Understanding how water behaves, understanding how pH, pKa, how titrations work of these amino acids. Okay? In addition to understanding the structures of them. It's kind of an important concept to have committed to memory. They'll go over this again. Okay? But again, it's nothing more than general chemistry. It's 400 level general chemistry is all it is. Okay? That's all we got. Does that make sense? Anybody want to grab a picture of it before I erase? I'm happy to erase. Okay, you want to get a picture? That's fine. Did you get it? All right. There are a couple of ways in which you can synthesize amino acids. And for the most part, you already know how to do this. You've just never made an amino acid from it. One way to do it is by using the Gabriel synthesis, which we've talked about before. What was the Gabriel synthesis useful for? It was good for making primary amines, right? What are most amino acids? Primary amines, right? So we just need to do some type of Gabriel synthesis. Does anybody remember what the starting material was for the Gabriel synthesis? Close. Okay, yeah, so phthalimide. Okay, good enough. So it was potassium phthalimide, and I'm drawing on the side, so it's a little strange to me. Cheap material. And it was reacting with what? Well, that's how we made this, was with the hydroxide, but we reacted it with an alkyl what? With an alkyl halide, right? And that gave us a primary amine after we deprotected the phthalimide. Here we want to make an amino acid, so we need some type of acid incorporated in that alkyl halide. And it turns out the easiest way to do this is to use our good friend malonate, or my good friend anyway. It has a bromine right there. So what's going to happen in that reaction? I mix the two together. How am I going to push the arrows, Ahmed? Yep. On what? The carbonyl carbon? It could. Yeah, but I got a good leaving group on that alpha group, right? And what's my leaving group? Bromine. So what kind of reaction is this? Just an SN2 reaction? That's right. And I don't want to draw all this again, so I'm just going to write PHT for phthalimide. It's just an abbreviation. Now I've got another acidic hydrogen here, right? I can remove that hydrogen pretty easily. What's the pKa of that, approximately, you think? 16 is a little high here. Okay, 13 might not be bad. Might even be somewhere around 11 or so. Okay? I don't know the exact value, but I know it's going to be less than sodium hydroxide or an alkoxide. So I simply react this with something like sodium ethoxide. I can deprotonate that, and then I can react that with some type of alkyl halide. Let's just make phenylalanine. It's a pretty easy one to make. So you start off with benzyl bromide. Benzene ring will just abbreviate as a pH. Is that an amino acid yet? Not yet, but it's got all the components that I need. What do I have to do now? Okay, so I need an amine, which I don't have yet, and I need one of these groups to be an acid. They're esters right now. So what I'm going to do is I'm just going to take this and I'm going to put it in HCl and water, and I'm going to heat it. What happened when we took malonates and hydrolyzed them to the diacid and then heated them? We decarboxylated, and we lost one of the carboxyl groups. And in doing so, we will end up with plus CO2 plus ethanol plus the phthalic acid that gets generated. All that comes off under these conditions, and I just generated an amino acid, in this case phenylalanine. What's the problem with this synthesis? Hard? I think I heard it. Well, it is kind of messy. That's not the real problem. What's the real problem?
Charge.
Well, I can change the charge, though, by changing the pH. So I'm not worried about that. It is multi-step. It's not stereoselective at all. What kind of product did I just end up with? Racemic. Are amino acids that we use in our body racemic? No. So I end up with a racemic mixture of this amino acid. So half the amino acid is actually unnatural. It's the D form, okay? And only half of it is the natural form, and I'd have to find some way to resolve it, right? So how might Aaron resolve the enantiomers from after the synthesis is over? How did we separate enantiomers back in chapter 5? That's going way back, isn't it? I don't need the exact technique, but how do we have to resolve, what do we have to do to resolve enantiomers? Pardon? Distillation won't work. Well, they will rotate light differently, that's true, but that won't separate the enantiomers. That's an analytical technique. Do enantiomers have different physical properties? Only in the optical rotation. Say it, John.
But diastereomers do.
But diastereomers do not, right? So we have to convert this into some type of diastereomer, separate them, and then convert the diastereomers back to the enantiomers. That's problematic, right? So wouldn't it be great if we just had a way to selectively synthesize one and only one amino acid? That'd be great, right? We'll talk about an example here in a moment, okay? So this is how you can make amino acids by the Gabriel synthesis, okay? You can also make amino acids using what I think is going to be our last name reaction, using what's called the Strecker synthesis. We will never have you do a Strecker synthesis as an undergraduate because the starting materials are actually quite toxic. You start off with an aldehyde. In this case, I'm going to start off with this aldehyde so that we'll make phenylalanine again. And in one pot, you react this with a mixture of ammonia and hydrogen cyanide. You all see why we won't let you do this chemistry? Hydrogen cyanide is what they put prisoners to death with. Right? That's the gas chamber gas, is hydrogen cyanide. And when we do this, you get this molecule. Is that right? Yeah, I think that's right. Does that look like an amino acid yet? What do I need to do to convert it to an amino acid? I've got the amine, right? What do I need? I need the carboxylic acid. How did we take nitriles to carboxylic acids? The oxidation state here for this carbon is the same as a carboxylic acid, remember? It was kind of odd that we talked about nitriles in the same chapter that we talked about carboxylic acids, but we did that because the oxidation state of that carbon is the same. So what do? We just boil it up in some acid. At least on paper, this is how it works. And you make phenylalanine again. Again, the problem with this synthesis is what? Besides that, you're right. But besides that, what's the problem with this synthesis? It's a racemic mixture. Again, you have the same problem. But how is this synthesis less messy than the previous one with the Gabriel synthesis? It's fewer steps. That's exactly right. Now, you're dealing with hydrogen cyanide, which isn't fun. Okay, but nonetheless, this works. Can anybody tell me how this step works? What's going on here? What's the intermediate? Cyanide will behave as a nucleophile. But if I have an aldehyde plus ammonia, what do I get as an intermediate? Close. What happened when we took an aldehyde and a primary amine? What did we get? What was the functional group? An imine, right? We're going to get an imine here. It's just with ammonia, not with the primary amine. And so what happens in the intermediate, you get that as your intermediate. Now, Jack, what does cyanide do? Cyanide is in solution, acts as a nucleophile, breaks the weak pi bond, and that's how you end up with the product. But it all happens in one pot, which is kind of cool, right? Then you have that, you put it over in some aqueous acid, you boil it up, and you have the amino acid. Okay? Pretty straightforward. But that's the Strecker synthesis. There are groups that have been studying how you can do the Strecker synthesis in a stereoselective fashion. If you can control the stereochemistry of the nucleophile attacking either the top face or the bottom face, you can control the stereochemistry of the final product. So there are groups that have been looking at making catalysts that will direct the orientation of the nucleophile one way or the other, or attaching some type of group out here that's chiral that you can then remove afterwards to do that. So people are looking at ways in which you can make these things stereoselective. In my group, we don't work with natural amino acids. We work with unnatural amino acids. And we use a process very similar to the malonic ester synthesis to do our chemistry. So we start off with things like diethylmethylmalonate, and we will treat this with sodium hydride. It's our favorite base, and THF. And then we'll add some type of alkyl halide. I'm just going to use benzyl bromide because we've been talking about that one today. What will the product be? Okay, right. So we'll end up with my methyl group will be here. That group will be there, right? So in one step, I've made the bonds that I want to make, but that doesn't look like an amino acid at all yet, right? Is that chiral or achiral? It is achiral, but I can get chirality pretty easily. We use an enzyme called pig liver esterase, and it will saponify esters at pH 7, okay, which is kind of unusual, right? It does come from the pig liver. When I first started here, we actually got pig livers and ground them up to get the enzyme, okay, back when I was really poor. That's what we had to do. And the pig liver actually has a lot of this enzyme in it, so it's real easy to get. And the enzyme is chiral. And so it will allow for the hydrolysis of one and only one ester to carboxylic acid. Now, do I have a racemic mixture or is it enantioselective? It's very selective, depending on what the groups are. I can get almost optically pure material sometimes from this reaction, okay? This reaction is pretty quick. Now I have optical purity, okay? So I've set my stereo center. What's going to happen if I react that molecule with SOCl2? To an acid chloride, right? And then I'm going to treat it with something like sodium azide. What's going to happen then? Not exactly SN2, but it's going to be a substitution, right? And it's going to replace the chlorine with what? With the azide. Yeah, we get what's called an acyl azide. And it doesn't mess with the chirality. then the magic happens. Okay, and I'm not going to expect you to know what happens in this particular case, but we take this and we heat it up in water. You can do this in water. Quite frequently we don't. And you get plus nitrogen gas. That's called a Curtius rearrangement. Okay. Strecker is the last name reaction you have to know, but this one, so it's called a Curtius rearrangement. And the cool thing about it is it doesn't alter the stereochemistry, so it doesn't racemize the product. And so now I basically have an amino acid that's just protected as an ester. I just simply have to hydrolyze the ester to the acid, and I am done. Okay? So the ones that you really need to know are the Strecker synthesis and the Gabriel synthesis. This is just me bragging about what we do in my lab. Why would this be an unnatural amino acid after it's hydrolyzed? What's unnatural about it? It's got a methyl group instead of a hydrogen on the alpha carbon. Why might that be important? Acidity is one. Two, it allows this to be more hydrophobic, which means that these amino acids can cross cell membranes better. And actually, some of these amino acids have been tested to detect brain tumors because they can cross the blood-brain barrier, which is kind of unusual for an amino acid. And so there's a lot of potential uses for these types of molecules. Okay? All right, that's it for today. On your way out, just leave your inverted lecture. Now, Wednesday, we will have our final lecture on this chapter, but also we're going to finish our last inverted lecture, okay, which has nothing to do with amino acids, but you have to be here to do it. So just come prepared to do something.